Alrighty, so we're starting Unit 7, which transitions us out of mechanics and into electricity. So we're going to be starting off with electric charges and forces, and then we'll get into electric fields and kind of the implications of electric fields. It's kind of broken into two chapters. Chapter 19 covers the electric charges and the forces. Chapter 20 gets more into electric fields, electric potential energy, electric potentials, and kind of that piece. We're starting out here with the idea of first electric charge, then we'll get into electric force, and then how we combined electric forces. From chemistry, you should hopefully understand that all matter has some form of electric charges. Protons are positive, electrons are negative, neutrons, they're neutral. But what we probably didn't get into in chemistry is the fact that electric charges can exert forces on one another. All right, so examples of this is if you take an amber rod or if you rub a balloon on your head and then bring it near some paper, you'll notice that when you've rubbed that rod or that balloon near some hair or some fur, it can become charged up and it will attract the paper. Other examples of this, if in the winter you walk across a carpet and then you touch a doorknob, you might get shocked a little bit because you've built up a static electric charge. And this has been known for a long time, way back to the Greeks. They're the first to figure out if you rubbed amber with the fur that it would become electrically charged. It's not just one type of charge that you can get. You can get positive charges and you can get negative charges, because I can either add extra electrons to an object or I can take electrons away from an object, okay, and make it positively charged. So as an example, if we took two amber rods or two pieces of amber, we hung one of them after it was charged, and the other one we just kind of hold on to so we can move it around like a wand. If I put those two like charges near each other, those two negative charges, extra electrons and extra electrons, they would repel each other. Now, on the other note, if I took a glass rod instead of an amber rod, and I strip some extra electrons off of it, so it becomes positively charged, it would be attracted to that amber rod. So the amber would rotate towards it and be attracted to it. There's different ways that we can actually produce a charge. Okay, so the first way we can kind of talk about here is what's called charging by friction and contact. So when you stroke a cat's fur, when you comb your hair, when you rub your shoes on a carpet or your socks on a carpet, you're actually stripping the electrons directly surface to surface. You're just ripping electrons from one surface, pulling them onto another surface. Okay, the material, it's a transfer of electrons between the materials directly. Okay, so for the example, we take that amber rod, you're stealing electrons off of the fur and putting them onto the amber rod. So you get extra electrons in the amber. The fur would actually lose electrons and become positively charged. Then we have charging by induction. All right. So when we notice that the rods there could possibly rotate, the negative attracted to the positive or the negative repelled from the other negative, that's what we call charging by induction. All right. But this can also occur with just things in nature. So if we have a thunderstorm form, what happens is you get these big updrafts. Okay, so we got a little cloud over here, and we have is a big updraft that happens in the cloud. All right, so we got the updraft of the air, and as those particles of ice and everything hit against each other, electrons get transferred. All right, so we get very positive at the top, very negative at the bottom of the cloud. But now the ground, we've had no kind of charging by contact happening with the ground. It's just within the cloud that you get positives and negatives. So that's why sometimes you'll just get that nice cloud-to-cloud lightning, right? So we're kind of going here, we're going zap to zap back and forth because the charge just within the cloud might transfer. But occasionally you'll get the cloud to ground because what happens is charging by induction. So because you got the negatively charged cloud top, or cloud bottom, I should say here, it causes the high points on the ground to become positively charged. So like tops of trees, tops of high buildings, things like that. And then zap, the electricity comes on down. The electrons flow through the air, which isn't really that easy for electrons to flow through air. It takes a lot of effort, which we'll talk about with the idea of electric potential a little later on this unit. But still, you can get them to eventually flow after you've gotten that kind of buildup. Said you're positive and negatives. Well, where did it come from? Oddly enough, Benjamin Franklin, one of our founding fathers. So he decided that he liked, when you charge up a glass rod, that should be called positive, and we charge up the amber rod, that should be called negative. Just his designation in his writings is what we still use today. That positive is what the glass rod was, negative is what the amber rod was. Now, atoms, we find out, are electrically neutral for the most part. And that comes from the fact that we have a dense nucleus that's positively charged, surrounded by this cloud of electrons. And it just happens that we have an equal number of negative and positive charges, so they kind of cancel out. And we say cloud there of electrons because, yeah, in chemistry we talk about these orbitals that they go around, but those orbitals aren't like set fixed orbits like the planets around, the sun. It's more of that at that radius, somewhere at that radius, you're going to find the electron. All right, it doesn't mean they're going in a perfect circle. They're kind of going more of a perfect sphere, cloud of this is where the electron is. Which is why you get those really funny shapes to the orbitals. So we did the SPD orbitals, and they kind of probably showed you the diagrams where they look like, balloon animals almost in some ways. The electron itself, we're able to measure its charge. So we've had different experiments done, and we find out that the magnitude of the charge, we're going to use this E for, is 1.6 times 10 to the negative 19 coulombs. So it's capital C is coulombs, and it's going to stand for that unit of charge, and it's an SI unit. It's named after a researcher we're going to talk about here in a minute, Coulomb, who did a lot of research figuring out how much force there was between charges. So that's why it got named after him. But it also brings us this interesting idea of what's called charge quantization. So have you ever heard of the term quantum mechanics? Well, all it's talking about is the fact that in nature, you can only have certain quantities or quanta of charges. Or even with atoms, you have certain quanta or quantities of protons or neutrons. Right? I can't have half a proton, or I can't have half of an electron. So for quantum mechanics, initially, some cool things came out, like the photoelectric effect that Einstein got his big Nobel Prize for, was just understanding the fact that, well, I have to have set amounts of energy or set amounts of charge there for each electron. So if I actually had a full Coulomb of charge, because one electron is very small, 1.6 of 10 to the negative 19, it would actually take 6.25 times 10 to the 18 electrons to make up that 1 Coulomb of charge. Now, to put that in perspective for something like really big, a lightning bolt somewhere between 20 to 30 coulombs of charge. So that'd be that number of electrons times 20 or 30. With most of the problem solving we're going to be doing, though, day to day, we're going to be dealing with microcoulombs. So a microcoulomb, you get mu's back to haunt us again, right? So if we look over here, we got our little mu symbol right there, right? Last time talked about mu. Mu is just for coefficients of friction. Well, mu is actually one of the SI prefixes, and it stands for 10 to the negative 6. So we're going to have microcoulombs will be like 10 to the negative 6 coulombs. Because most of the charges that we'll be working with here are going to be very small charges, because we're going to deal with realistic charges that you might build up on a balloon or on a Van de Graaff generator, which is another device we'll talk about this unit. Again, electrons have a negative charge, so it's really negative of that E. Okay. Now the mass of an electron is very small, 9.11 times 10 to the negative 31st. Proton will have a positive of that E. Okay, but its mass is a lot bigger. Neutrons, they have no charge at all, and their mass is still a little bit greater than a proton. Partially due to the fact it has to do with the charge piece, but it just gets into some stuff with quarks, that they're made of slightly different quarks. One other thing we're going to be talking about a bit is the idea of things that can conduct and things that insulate electricity. So if the atom allows one or more of their outermost electrons, those valence shell electrons, to become detached, we start to call those conduction electrons, because they can freely move throughout the conductor. They can get passed along from one atom to the next atom, and we can pass some charges along. Okay, we can conduct electricity, we can conduct charges. Whereas an insulator, very few of those electrons are free, and they insulate well. Basically, they don't allow the electrons to flow that well. So if you're looking at a periodic table, generally, metals, those are the ones that have those free valence electrons, those outermost electrons that can detach, and they conduct very well. The insulators, you get to the extremes, okay, on the periodic table. So those are normally things like the noble gases and way over there. They don't like to allow things to move that well, all right, because those outermost electrons are very bound. So then we got another really interesting concept to talk about, and it's really only been in the 20th century and forward that they've been a big issue, which are semiconductors, okay? So semiconductors are solid substances that have a conductivity somewhere between an insulator and a conductor. Okay, so we start talking about things called conduction bands, and basically how well do they conduct? And they'll conduct, but they're not as insulating as an insulator, but they're not as good as a good metal. And it's normally because there's some impurity that's in that material. And a lot of those impurities are the transition metals on the periodic table. And some are affected by temperature, some are affected by just, adding a little bit of extra charge to them. The most important one for us has been silicon. So basically every computer device, starting from like the 1960s forward, the transistor, that was the big thing. We went from having to use big tube radios, tube televisions, to small little transistors. You could get small portable radios, small portable technology. Once we were able to start to understand how semiconductors worked, and we were able to reduce the size of our electronic circuits. And then eventually we were able to build computer circuits from that. And it basically deals with the fact that outermost energy state, if we properly excite it, we can either make it behave like an insulator or make it behave like a conductor. Basically, we make a switch out of it. And that's what a transistor does. It transitions between acting as a conductor and acting as an insulator by giving it a little bit of a charge, so what they call like a switching charge. Now that we've talked about what the charges are, what the types of materials are the charges can be on, what actually happens between charges? Well, that's the electric force. So, a man by the name of Coulomb was who did our research in this area, and he started thinking about, well, what if we have two electric charges? And we're going to call them Q1 and Q2, because we don't want to confuse ourselves with more C's here. So Q is what we're using to represent a charge. And he realized that, well, if you doubled the charge of one, the force doubled. And if you doubled the force of the other one, or the charge of the other one, the force also doubled. So he realized that there was a proportional relationship right here, right, to the charges. So the force was proportional to charge 1 times charge 2. Okay. Now we also noticed that there was an inverse square law relationship. So we noticed that as we took those, charges and we separated them, the further apart they were, the force reduced. Just like it did for gravity. Okay, so if you remember when we said gravity, the further apart they were, we went down by a 1 over d squared relationship. It's the same thing here for Coulomb. All right, so as Coulomb's law kind of states, or his observation stated, that the force is proportional to 1 over d squared. Okay, so it's this inverse square of the distances separating the two charges. Okay, so again, that'd be like if I had my kind of Q1 here, my Q2 here, the distance would be between the two. Coulomb then combined these two laws. So first I realized, or the two observations into a law, I should say. First he realized the force was proportional to Q1 times Q2. Then the force was proportional to 1 over d squared, that inverse squared law relationship with distance. And then he realized, just like Newton did, there had to be a constant to make it equal. Okay, but unlike Newton, he actually took the time to find his constant. And he found this constant, lowercase k, which is known as kind of the Coulomb's constant for force, which was 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Now, don't get confused for those of you who might be taking AP Chem. There might be another Coulomb's constant gets mentioned, which is a relationship between how many actual electrons are in a Coulomb of charge, which we kind of already mentioned before, previously. So we get to this equation, F equals K, Q1, Q2 over D squared. So now if I know Q1, I know Q2, and I know the distance, I can figure out how much force there is between those two. But here's the thing that's special. That is only a magnitude equation, because if they're two positive charges, they're going to repel. like it does here in case A. If they're two negative charges, they're going to repel, like it does here in case C. But if one's a positive, one's a negative, they're going to attract. So it becomes very important that we actually diagram these out to figure out, well, what are the charges? Will they repel each other? Will they attract each other? So we figure out what the force is, on charge 1 from charge 2. So if you notice, there's like little subscripts up here. Okay, so when I'm looking here, little subscript there. And what that's basically saying is the force on 1 from 2. Okay, that's why it's F sub 1, 2. All right, whereas the other one on the next side says F 2, 1. That'd be the force on 2 from 1. All right, just kind of get into the nomenclature of how we're designating these forces. So for case A and case C, the force on 1 from 2 is negative. But we get to case B, the force on 1 from 2 is positive because, in that case, it's an attractive force, not a repulsive force. Now, we need to remember a few things here. Because we have a magnitude and a direction, electric force, like all force, is going to be a vector quantity. Okay? So when we have those charges that are experiencing forces due to 2 or more other charges, we might have to do a vector sum of those individual forces to figure out, well, how will that actual charge go? All right, and I'll show a little diagram of that in a second. So we need to remember again, the total force acting on a given charge is the sum of all the individual forces between the 2 charges at any given time. Okay, so what that means is, let's say there is actually 3 charges. So I've got charge 1, charge 2, charge 3. Well, there could be a force on 1 from 2. There could be a force on 1 from 3. All right? That will give me the net force if I do vector addition of those 2 forces. That's how I'd actually find the total force on object 1, or charge 1. All right? So, I mean, once we get a little bit more practice with this, it'll make a little more sense. But again, this is just the first of the concepts we're going to be going through.